Hey, and welcome back to Quick Math with me, Quitch. So the last video I posted, we talked about what open sets in the Euclidean spaces are, and today we are going to riff a bit more on that, specifically on open sets in the real numbers, but this can also be generalized to any Euclidean space. So what we want to investigate today is that given an open subset A of the real numbers, what we kind of want to investigate is how can we write this set as a union of other subsets. And in specific, what we want to show is that A can be written as a union. And not just any union, as a countable union of intervals, open intervals even. Let's start by recalling what it means to be open. A open means that for any x that is an element in A, then there exists some small, or doesn't need to be small, but in general we'll think of it as being small. There'll be a small interval, right? The interval from open interval around x, such that this is entirely contained within the set A. So one initial strategy we could take is that if we let this interval, if we just call this, we can give it a name. Let's just call it I, and it will be indexed by x, right? For every x in A, there will be such an interval. So what we can certainly do is, if we take the union of all of these, right? So we take a union over all the x's of A, and for each x, we take this interval, and then we take the union. So this, I claim, will in fact be equal to A. If we have an element in the left-hand side, the union, right, then because all of the intervals there are contained within A, so that means that if you take a union over such a collection of sets, it'll definitely be a subset of A. So this establishes this inclusion. And on the other hand, given an element x of A, well, we know that x is an element of the interval Ix, so that means that also trivially the other way around. So this is a way that we can always write an open set like. The problem with this is that we were kind of looking for a countable union. And since we don't know nothing about the size of A, the set, then this is not necessarily countable. Okay, so somehow we want to thin out this union. So can we do better? Can we write A as a union of open subsets that will always be countable? Well, so let's start again. Let me be taking an arbitrary x within A, and just like before, we know what does that mean. That means that if you have x here, then there is an epsilon, such that this entire open interval, right, is entirely contained within A. We will use the fact that the rationals, they are dense in R. What does that mean? That means that given two real points, we can always find a rational number between them. So what are we going to choose? Well, consider the interval here. So this will, so you imagine that this is x minus half of epsilon. This is x plus half of epsilon, right? So well, this is an interval. That means we can always pick a rational number that is within this interval. Let's say it's here. Then we'll give it a name. Let's call it xq. Q for rational, right? This is squeezed in between x plus epsilon half and x minus epsilon half. So what we want to do now is we'd like to create an interval around this new point, this rational point. And we want to not only should it be an interval, it should be an interval with a rational width or rational radius. And we also wanted to include the original point x. Okay, so we are looking for a rational epsilon. Should be positive as well, as epsilons are. We want x to be in the interval, so we require that the distance from x to xq, we need the epsilon to be, well, it actually needs to be bigger than that, right? Otherwise, we'll get an interval with which x is not in. We also want this new interval, this rational interval, if you will, we want it to be within the original open set around x. Right? We can achieve this by requiring epsilon q to be less than the original epsilon halves again. Right? So, and once again, because the distance from x to xq is a real number and epsilon half is a real number, because the rationals are dense in q, we can now pick an x between them. And of course, I should add that the distance from x to xq is of course less than epsilon half, right? That's how we chose it. And that means that this distance, it will be less than epsilon half, so therefore we can squeeze this rational epsilon in between the two. Okay. So what do we have now? Now we have an interval that looks something like this, right? It's centered around xq and it has a radius of this new epsilon q. All right, so we have already chosen epsilon q such that a is indeed a member of this new interval. Let's give it a name. IQ, a very smart name. But we've already shown as that this the original point x is indeed a member of IQ. Okay, but we also want to make sure that this new rational interval is within the original interval around x. So in order to show this, look at an arbitrary element. Let's just call it x0. It's an arbitrary element here. And what we want to show then, of course, is that for it to lie within the original interval, what does that mean? Well, that means that we need for the distance from the original x to x0, that should be less than epsilon. The question is, of course, is this true? Well, what we can do now is we can use the triangle inequality. It seems like I'm using the triangle inequality in my videos a lot lately. So, hey, it's a wonderful tool. So, as usual, I like to think of it as we are taking a detour. So instead of measuring the distance from x to x0, we kind of bound that distance between taking a detour over this new point x. No, not a new point, of course. We wanted to take the detour over x cubed. This is the triangle inequality. And of course, now comes the clever part. Already we've chosen x minus x cubed. That's already chosen, so it's less than or equal to epsilon half. That's what we did in order to make sure that x is in I cubed. So we can bound that by epsilon half. And then we have the distance from the rational. Oh, I can see. Silly me. Should have, of course, have been like this. So what about the distance from x cubed to x0? Well, we know that this is within, x0 is within I cubed, and that means that by construction, this is less than the rational epsilon, right? Epsilon cubed. Finally, we have this epsilon cubed, but we also know that is chosen to be less than epsilon half. So that means this is all in all less than epsilon half plus epsilon half, which is of course exactly equal to epsilon. So what have we shown? Let's take a step back. We have shown that for, we have showed that for A subset of R, an open set, and X is an element of this open set, then there is not only an open ball, an open interval, but a rational interval. Let's call it Ix. Slightly changing the notation. I hope it's not too confusing. But it's an open interval from P to Q, where P and Q are both rationals, and such that X is an element of this interval. This is quite a bit stronger than the original definition of an open set. So what is the point here with that? Well, remember that originally we wanted to write A as a union, and what we did is we took X over all of A, and then to each X we associated an interval, and we're doing the same thing now, except that this Ix, these are now all rational intervals. But let's consider the set or the collection of all rational intervals. Let's give it a fancy name like IQ, fancy I and Q. So how we will write it is the collection of intervals from P to Q, where P and Q are rational, and of course P is less than Q. But the big idea here is that if we look at this set, because remember that Q is countable. Q is countable, and that means that this set, which is basically has the size of Q times Q, is also rational. Not rational, it's also countable. So if we go back here, right, we have that A. So it's still a union over all these intervals, but all these are x, there are elements in this countable set of rational intervals. So A might possibly uncountable. But remember that these Ix over here, they all come from a countable set, countable collection. That means the Ix's, they'll have to be duplicates of these sets, so that in the end, there's only a finite number of them over there, right? So there is a countable number distinct elements of the set of rational intervals. So we kind of shown what we wanted, that A can be written as a countable union of open sets. So this is very nice, I guess, but why do we care? Well, it's going to be practical results in many ways, but here what I want to discuss is a property of certain spaces, in general topological spaces, but don't worry about that if you don't know what that means. But we say a space is second countable. Don't worry about why the name is as it is, but a space is second countable if there is a countable collection usually called B, because it's also called the basis, such that any open set in the space can be written as a union of elements in B. So in other words, an arbitrary set, we can write that as a, well, it's a countable or possibly finite union, but that's just rounded as countable. And what should we call this? Maybe that's BI, where all BIs are elements in this set B, the basis. And now we've done all the footwork to show that, well, it's practically a corollary now, right? That R is second countable. And why is that? Well, as the basis, we can now choose this collection of rational intervals. And we've just shown that any open set can be written as a union of elements in B. So this is a very important topological, as I said, property of the real numbers, and this can be generalized. It turns out that Rn is also second countable. This is a property we'll use both in the measure theory series, and it is also an important property of manifolds, which are the objects of study in differential geometry, which I also hope to come back to. And then finally, as you may or may not have heard, you probably have, is that Dolly Parton passed away yesterday, this time of recording. So I just want to say Rest in peace, Dolly, and we will always love you. See you in the next one.